since our classes have been so spread out, so I kind of like to, in a way, to summarize what we are actually doing and where we are going very quickly. So to be able to start solving boundary value problems, we need to have 3 ingredients. And that's what we have started doing a while ago, and then we had a lot of snow days, cold days, all sorts of things. So the first thing that we needed to do was this strain deformation relationship, right? We derived these equations. Do you think you can write it on your own? Do you remember how strain relates to displacement? Try to retrieve it from your memory if you can. If not, look back at your notes. If I write it, you all hopefully recognize this. So we have started with displacement gradient, and then I showed you that the skew symmetric part is just infinitesimal rotation. So we need to look at the symmetric part, and this is what it is, basically. So don't forget that all of the things that we are doing is actually valid when the gradient of displacement is very tiny. So we have infinitesimal displacements. And then another very important relationship that we talked about over the last 2 classes are those strain in the same kind of strain deformation relationship is the strain compatibility equation. So does anyone remember what does this guarantee? Let me write it first, and then you have time to think about it. So I write the equations which are, this of course I don't expect you to recall because it's kind of complicated. When I'm not sitting or standing up front, I can actually write it, but so what does this guarantee? What is this equation? Do we remember? It had something to do with the students who were blue. Remember? I made an example. Yes, Kingsley. Yeah, so what does it say? What is the concept? What does it guarantee?
It guarantees that the displacement is continuous.
It's single valued. Yeah. We have a continuous displacement, and more importantly, there is a displacement field from which we have derived these strain tensors. So that is what it guarantees. And we had you have basically 81 equations, and out of them around 6 are, even these 6 are not completely independent, but normally we work with these 6. And I have written down only those 6. K is equal to L. So this was, if you want to look back, this is chapter 2 of the book. And we already talked about it. And then I kind of cut the corners because of the snowy days and so on, and I went through the balance laws pretty fast because we don't really deal with them in this class. If you really like them, if you really want to see where they're coming from, you have to take continuum mechanics. But what we deal with this here are Cauchy laws. So the second kind of important aspects that we need to look here are the equilibrium equations. this is the second ingredient. So I need first ingredient, it's that. The second ingredient are the equilibrium equations. Now, try to see if you can write the Cauchy equation, if you remember. Would be useful to remember because you are going to see it everywhere from now on. If you don't remember, don't worry about it. Look at your notes. See if you find it, you know where it is. So we had like 3 equations. One was a consequence of the balance of linear momentum. And this is, it looks like this in that's when we don't take into account acceleration. Everything is happening very slowly. And very important in tensor, in index notation, this is how it looks like. Right? And we kind of remind ourselves that since everything is very, very small, so again, this assumption is everywhere, then we are taking all the derivatives in reference configuration because the reference and the form are very similar to each other. What was the consequence of the balance of angular momentum? The symmetry of the stress tensor. So exactly. And then we had another relationship which relates the stress tensor, to the traction. And we used T for traction. And traction, remember, is force per unit area. So ingredient number 1, ingredient number 2, and number 3 is what we are going to do today. Before I forget, this is chapter 3. So if you got the chance to look at the next homework, which is homework number 4, there are problems from chapter 2 and chapter 3, which you can see here. And today what I want to talk about is the stress-strain relationship. And there will be no snow on Thursday. No way. Right? Everything is going to come tomorrow, and Thursday is going to be sunny and beautiful. This is chapter 4, a stress-strain relationship. So just that you know where things are in the book. And from chapter 5, so we start basically solving problems. Before going to a stress-strain relationship, which will be the bulk of this class, there is one concept that we need to carefully look into. Oh, what did I do? Probably I can copy paste, right? Copy. Yeah. Okay. Great. So I went to the last page. And that's the concept of a stress. So what is a stress? And this will be very short, but it's an important thing. So we are, to be able to define a stress, I mean here we mean Cauchy stress. We need to look at this relationship again. And what is TIN? It's the traction per unit surface. So You can call it per unit area. And remember that we define traction at the boundary. So if you have a point, this is the boundary of the object. We always used delta B. And we have, here is, for example, a traction. And we use the normal to the surface, like n, to define the direction of the boundary like that. So traction, TIN, is force per unit area. Then what is then a stress? I bet that a lot of you learned a stress as being force per unit area. But looking here, what is force per unit area is actually TIN. It's not a stress, right? What type of object is a stress? It's a tensor. And what did we define tensor before? So what is it mapping? Now look here, I think this is Mustafa asked me this question like after the second class or something. So a stress, what kind of vector is it mapping to what kind of vector? Let me ask you this. What is the object TIN? What type of an object is it?
Vectors.
Forces are vectors. Forces are vectors, no problem. And this is force per unit area. So now if someone asks you in a cocktail party, what type of object is a stress? You say it's a tensor, and that person says, no, it's force per unit area. You say, no way. Actually, it's a mapping. It's mapping what to what? Can you tell me? Take 30 seconds. Talk to each other. It's fine. So it's mapping what to what? Thomas. Who? Who was first?
It's mapping the direction, normal vector to traction.
Exactly. So it is mapping the normal to the boundary to the force per unit area. And that's why it's a tensor. Okay? So it's mapping n into forces. So I don't know if you go to these kinds of party, but maybe there is someone in this party who says, come on, we all know that tensor is force per unit area. Look at the unit. It's force per unit area. What do you answer? They even ask you, did you take elasticity? You say yes. So, well, how would you answer to that question? I have a good answer. If you went to this party and you met this guy asking you, so consider moment of a force. What's the unit? Force times distance, right? How about energy? What's the unit? Are they the same thing?
No.
Not at all. That's the answer. So, and then you just say salute, and then everything is fine. The whole thing is resolved. So, we learned that a stress is not force per unit area. And what is important here, besides joking about it, is that when we define boundary conditions, the boundary conditions are not in terms of a stress, they are in terms of traction. So we don't have a stress boundary conditions, we have traction boundary conditions. And it is important, and they are very different, because look, how many components of a stress do you have? Consider symmetry. 6. How many components of traction do you have? 3. These are two different problems. You cannot say, well, I have a stress boundary condition, but you define traction or vice versa. So it's an important distinction to make, and it's a graduate kind of definition for a stress. So you now, I hope everyone is convinced that this is a tensor for now and forever, right? I really hope you don't go to these kinds of gatherings. So, and some other things that you may see in derivations are something called normal stress or shear stress, which are also, in a lot of cases, they are actually forces and they are not really a stress. So when people talk about normal stress, what they're actually doing is they're projecting the traction along the normal to the boundary, or they're projecting it in the tangent direction to the boundary. So if we call one component n, and that would be just Tin. Well, I should not write it like this, half and half. Tn dot n, and sometimes people call it, this is what they call normal stress, but this is really a component of the traction force. And the other component, the magnitude, would be just, so you have the magnitude of Tn. If you take n out of it, then you have shear stress. This is what people call shear stress. But now we all know that the distinction between stress and traction. So that's why I put them in quotation. So what we have are actually components of the traction force which are normal or tangent to the boundary. So it's important that you make these distinctions. So maybe I write it here. So this is just component. It's not a real stress. Component of Tn normal to the boundary. And this is the same. Tangent. Okay. So another thing about a stress which we need to kind of use later on before moving from chapter 3 to 4 is similar to a strain. You can also write the stress in terms of the summation of a deviatoric and a spherical stress tensor. So I use the same notation as before with tilde and hat. And I hope you remember that the spherical or hydrostatic, it will be very similar. So instead of E, we just have and a definition that it's useful in a lot of applications is this notion of pressure. And I'm sure you have seen this before. And that is basically minus 1 over 3 sigma kk so that we can write the hydrostatic stress in terms of pressure. This is useful. And if you have looked at your homework, one of the homework uses this, one of the homework problems uses this notation too. So now we are done with everything I wanted you to know from in chapter 3, and we are moving to chapter 4. Okay. Now remember that we want to solve boundary value problems. So the equations that we have, I just reviewed for you. The Cauchy equation, the balance equations. How many equations do we have? This is an equation. It's only 3, right? We have 3 equations, and how many? What is given here? Is f given or is it unknown? It's given. How about sigma? I guess I should move back a little bit and ask you this question. When we solve an elasticity problem, what are we looking for? Displacement or a strain or deformation. I mean, a strain, deformation, it's the same thing, or a stress, right? The forces are given. So if you look at these equations, we have 3 equations, we have 6 unknowns, right? So if you want to solve for stresses, we can't really do that. So we need some other equations to supplement the equations that we have. And those are the materials behavior equations. So with that, let's start to look at constitutive laws. So this is a linear elastic class. So everything that we talk about here is really for materials which are linear elastic. So what does it mean? Let me write down here that this is chapter 4. You all have seen linear elasticity before. What is it? What does it mean? How would you define it for someone? Yeah, but we want to now make everything a little bit more accurate. So if you are talking about a strain, it's a small strain, infinitesimal strain. And a stress, we mean Cauchy stress. This is what we mean. So I just write this down, just what you said. So we assume a linear relation between Cauchy stress and infinitesimal strain. I told you before that when you talk about anything linear, it's linear in something. So a stress is linear in a strain. We cannot just talk about linear by itself. So we already know what is a stress, how to write it. It's a second order tensor. I hope after today you will never forget why, right? And then a strain is also a second order tensor. So now, what would connect a second order tensor to a second order tensor? A fourth order elasticity tensor. So here it is. Perfect. So this is called elasticity tensor, and This is sometimes called, you have seen it before, generalized Hooke's law. So, it's very simple, but it turns out that in the lab it can still explain a lot of properties for a lot of useful materials. As long as we are in the small deformation regime. So that's kind of the caveat here. So what does it predict? So if I don't have any strain, could I have any stress or vice versa? No. So one of the kind of pillars of linear elastic material behavior is that if we don't have any strain, we also have no stress. It's kind of obvious, right? So sigma ij is 0 if EKL is equal to 0. So that means we don't have any stress in the reference configuration.
Is that a requirement for this?
It is given, right? That's the relationship is telling you that. Can you have anything else?
Well, if you have like a pre-stressed specimen.
Yeah, so that's exactly where I wanted to go, and you're jumping the gun. Exactly. So is this always the case in our materials? No. Do you have in your research something specific? Do you want to share it with the class?
Well, it's just, I work with composite materials, and sometimes you can apply pre-tensile stress to the fiber and then release it after you set it in the matrix, and it'll apply like a constant compressive load, for example. So you take that as your reference configuration, but you have a predefined compressive stress and everything.
Exactly. So you have some sort of, can we call it a residual stress?
Yeah, I was trying to do that.
So a lot of materials, you have some sort of residual stress in them. So your reference configuration is not really a stress-free. But this theory, if you don't have any stress, you cannot have any strain. So this theory is not explaining everything you have in reality. I just want to make a distinction between the limitations of the theory and what you have in reality. A lot of times you have pre-stressed or what I like to call residual stresses.
After you need it.
Yeah, if you can unload it, yeah, if you can relieve, there are methods to relieve those residual stresses. But so that's one of the things that this theory does not take into account. Gerald, you are not sure about that? It's just if it is 0, the other will be 0. So you can, if one side is 0, the other side is 0.
Right, so residual stress, the material completely elastic then? You have it?
So, yeah.
If after you draw the stress profile, you divide section, it has elastic portion and elastic.
It's very hard thing like you plastically deform it, but it can still be elastic after you deform it.
Exactly. So there is no strain, but there are some residual stresses inside the material. To start with, yeah. So, yeah. So how about, for example, I mean, one example that maybe Gerald can talk to you is when you look at cracks, like in solids, a lot of times they're like closed cracks. You really don't have any strain, but there is residual stress at the tips of those cracks. So if you have a way to measure the stress, you have actually a stress there. So it's plastic, it's not elastic.
Right. So
that's why this theory is not good for it. That's the whole point I'm making. Exactly. Yeah. Another thing, if you have any kind of material that it's rate dependent, could you use this theory for that? So if the response of your material depends on the rate of loading you apply, you can. Do you see a time here?
So like viscoelastic.
For example, viscoelastic material. There is no time here, right? This kind of model is only good for something that reacts immediately. So that the moment you apply the force, it reacts, and the moment you remove it, it goes back, because you have a stress-strain relationship which is linearly related. So you cannot use that for something whose behavior is rate dependent. So just to make sure, so no rate dependence is built in this model. It's a material model, right? And no path dependence in the sense of loading path. What am I talking about here? Path dependence, loading path. Can someone give me an example of a situation where the behavior depends on the loading path? Someone who hasn't talked in this class so far and is not too tired to talk. Two conditions. Is it clear when I say loading path? Have you heard of hysteresis? What does that say? I mean, if you have loading and unloading multiple times, the behavior. Sorry, someone was. Exactly, you have hysteresis. So in this model, none of that. If you have a material which has a strong path dependence, you cannot use this kind of model. It's very simple. And this implies that now, since we have no path dependent, we can no. So that's a different thing, and we get into that. So this is about the model, like how the model is it works. This is just that it doesn't have any memory. There is no. You cannot use this model to model anything which has a memory, the material which has a memory of the previous deformation in it. Now we get into isotropic. You can have a material which is anisotropic, but it can be linear elastic. So I kind of see them as two different things, and we get to that. That's the fun part of this class, to see how mathematically we can look at isotropy and anisotropy. There's also some words which are somewhat hard for me to get right. So, since there is no path dependence, we can write the stress as the derivative of a potential function. This you are familiar with. We can always do that, right? So there is a scalar function u such that we talk about more about this scalar function later, but from your previous knowledge, do you know what this function, this mysterious function u is? It's a strain energy density. It's a strain energy per unit volume, right? We talk about this a little bit more later, but I kind of need this. You will see in a moment why. So this is elastic, because we are in the realm of elasticity. Elastic strain energy density. It's I shouldn't go towards the edge. And when I say density, I mean per unit volume. Okay. So this I write this as one equation because we need that later on. I give it an asterisk. And since we know the relationship between a stress and a strain, then if we use this equation, then we can write U as this is of course if it is constant, but we get to that. So what we want to focus on right now is this fourth order elasticity tensor. How many components does it have? 81, right? So this elasticity tensor in general has 81 but so now if we know some symmetries, right? We know that the stress and the strain tensors, they are both symmetric. So let me write the relationship between, write it here so we have it. This should have been in orange, but it's written here. Since a stress tensor is symmetric, what can we say about the symmetry of the elasticity tensor? We can switch I and J, right? That's one symmetry we have. And you can see where I'm going. The strain tensor is symmetric too. Write down what type of symmetry you see in elasticity tensor on your own. I hope it's like that. There's another symmetry which is not as obvious, and that's why I defined the strain energy. So if we go back, you can think about the elasticity tensor as the derivative of a stress with respect to a strain, right? This is something you are familiar with. Now, if I use the fact that we don't have any path dependence and we have this mysterious U strain energy function, so I just put the equation that I give it a star before. You can write this as the second derivative right? Now, I guess you see what I want to do next, right? I want to use the fact that U is a potential function. If it is differentiable 2 times, can we switch the two? Yes. And can I write this as KLIJ? So this is another symmetry which was not as obvious as the other ones before, and that's why I had to define very quickly and briefly the strain energy for you. Now we want to see with all these symmetries what happens. So since, let's write it, all these symmetries. Since we know that we can switch I and J, and we can switch L and K, and not only that, we can switch the pairs based on what I showed you above. The maximum number of components that we can have is actually 21. Maximum. Independent, of course. Independent. Elastic. And you know that we call these components elastic moduli. I didn't tell you before, but I assume everyone knows that. It's actually not 81, so even if you have a lot of, the most general case, you cannot have anything more than that. And this is because of all the symmetries I showed you. So it has nothing to do with materials here. Okay, now the fun part. Trying to relate the things you know to the mathematical representation. Any questions so far? This should be familiar to you. Somewhere in your history, you have seen these things. Maybe not in this form, but something similar. Okay. Now I want to talk about something which I think is very important in an engineering class. Almost everyone is engineer or scientists also, like. So material, when we say a material, now linear elasticity is a model. Now I have a material which is homogeneous. I want you to think, what does that imply for the elasticity tensor? So let's not talk about it now, just taking like a few seconds to think about it. I just write, so you have a material which is homogeneous. What does it mean even when we say homogeneous? No. Well, that's the thing. We are in a graduate class, the door is closed, no one is saying, I know that I'm recording, but I don't think anyone who really doesn't have to look at these videos will, so we are safe, right? We are safe here. There is a lot of confusion even in graduate class between homogeneity and isotropy and so on. So that's why I want to, just like a stress, that I hope we close the door to a stress being a tensor today, I want to close the door on homogeneous and isotropic and what it means in terms of elasticity tensor. So that's why I'm bringing this up here. Homogeneous material, if you want to talk about it in a meeting, I don't want to use that party again because that would look like a real terrible party. So how would you define a homogeneous material? Talk. Exactly. The material property is basically spatially the same, right? That's what it is. So properties do not vary spatially. So this is kind of a fancy word to say that, everywhere you look, it should be the same location. So tell me, what does it mean for CIJKL? But someone who hasn't talked, I feel like there is a cluster of very interactive group, and then I like to see people who haven't talked. And I know all your names, but I'm not using anything like that, right? What does it tell me about CIJKL? Alex. Exactly. That's what I wanted to hear. So that means they are constant. It's not a function of position x. If this was not homogeneous, CIJKL could be a function of x. So if it was not homogeneous, this would be a function of x. If it is homogeneous, that means this is constant. I know that you have always seen constant moduli most of the time, but it's because most materials we consider, or many of you consider, are actually homogeneous. But you probably didn't think about it. It doesn't have to be. So we have 2 geoscientists here, right? At least. The materials that you deal with in geoscience are good examples of inhomogeneous materials. So just consider the Earth. As you go down, the material properties are changing, right? So if you want to model the Earth, you have to consider this inhomogeneity. And then CIJKL would be just a function of, for example, depth or location. So this is not given. Any of you works with any kind of other materials which is not considered homogeneous? Mm-hmm. At different location, or is it at different direction? Okay. Okay. Perfect. Exactly. The reinforced concrete is exactly like a heterogeneous material. Composites are good examples, but they're also good examples of anisotropic materials, which we get to that definition. Great. So I hope this closes the. Always you remember homogeneity is really different from. It's just about a spatial distribution. Now we go to the second one, which people always mix up, and that is anisotropy, right? So let's talk about anisotropy first. What does it mean? Exactly. So it has something to do with orientation, not necessarily the spatial location, right? You can be at one point, it can be exactly the same everywhere, but in different directions it's different. Right? So properties, so I just to be the same, similar to homogeneous material, I would say properties vary with direction or orientation, whatever you like better. And Tom already gave us some examples. Composites are good examples. Any other examples that you can think of in your field, whatever you are working on? Wood is a very good example. You all have seen wood, right? In the direction of the fiber or perpendicular, you have very different properties. I know why you are that. So crystalline minerals, right? Crystals, they can be very anisotropy. So if you have isotropy, is kind of the opposite of anisotropy, right? So now I know that a lot of you are from, departments who deal with metals. So metals, you have a lot of grains, but most of the time we consider them to be isotropic. Why is that? Cody. No, sometimes if you even want to look very closely, I know what you are talking about, but if you even look very closely, would you consider them anisotropic? Let me ask you this question. Imagine you are looking very, very closely. If you look around, do you see any difference in different directions? There are some differences, but those differences are random. Exactly, you want to add something to that?
So I was going to say generally there's a manufacturing and material of the grain, the distribution of the grain orientation is more or less random.
Exactly.
So at a macro scale, the bulk properties and things like that as well.
Exactly. So then now, going back to what Cody said, if you go inside one grain, then it's different, right? Then you have a crystal and it's different. But if you look a little bit further, you have random distribution, so it doesn't matter which direction you are looking at, right? So most of the materials are actually isotropic. I know that in geoscience it's not the same, but even when you don't have isotropy, you have isotropy in a certain direction. For example, in rocks, the vertical and horizontal are very different from each other, right? But in horizontal direction, if you look around, you can assume that everything is the same. So you have some symmetries in the material. Now, so I guess this is clear to everyone. But what is important now, going back to what I asked you before, how would we define this mathematically? What does it mean for the elasticity tensor? That's where it becomes fun, right? You have to draw from the things you have learned before. What does it mean for the elastic tensor if the material is isotropic? Exactly. So what does it mean? If I rotate it, what would happen? It is the same. Could you write that down? I've taught you this. You know how to rotate a fourth order tensor. I even asked you to write it down in the class. How many Q's do we need? 4. Let's write it down. You have seen this before. So try to write this being direction invariant on your own. So it means that elasticity tensor is rotation invariant. So if I take this tensor CMNPQ, if I want to rotate it, I need 4 Q's. I'm going to get another tensor. I called that prime before, right? Prime IJKN. Remember this? I hope you remember. I feel like whatever you have done on your own, you remember. This is kind of my hypothesis. I think this is the case. Now, if it is it true? No? some depends on the hour, you know. So if it is isotropic, what should I do then? That means that there is no prime here, right? It's the same, it becomes the same tensor. Tensor IJKL is not different from MNPQ. This is the same C. So if I rotate it, doesn't matter how, it will still be the same elasticity tensor. Is this clear now for everyone? Can you connect it to the concept easily? Yeah. Right. So it even becomes better. So you see now something that you have seen before, and you complain a lot about it. And now I will write it down, and you all remember, I'm sure. Because homework problems, you remember them, especially if they have been a little bit, I don't know, problematic. Let's put it this way. It turns out that the most general isotropic elasticity tensor has this form. So it can be shown that, you know, these sentences, it can be shown. I'm always afraid when I read a book and I see this sentence, it's very scary, because if you try them, they're typically dreadful derivations. It can be shown that, right? The most general form that satisfies, let's give this don't want to write it down, is this. Do you remember this? Does it look familiar? I've been excited the whole day to show you this. So you see that what you were doing was not for nothing, just a mathematical exercise. And you have actually shown that, all of you. You showed that if you do that transformation, you get the same thing. Some of you, I don't know why, but a lot of you really chose a very hard way to do it, and some of you use but you all have shown that. So it turns out that this is the case. Right. Now, substituting this equation in sigma aj so we limit ourselves in this class to isotropic materials. So we know this is the general form. If you substitute it in linear elasticity, you are going to get something which is much, much simpler. Any questions so far? Anyone who doesn't remember this and didn't share the common joy of the class? I think it's great when you see, that you can see things. Okay. So now, if you substitute, what is happening? So if you substitute that, and I suggest you to try it. It's very simple. You get an equation which looks like this. So everything collapses to something much simpler. So this is for linear elastic isotropic homogeneous material, right? Where mu and lambda are called Lammers constant. And I'm using tensor notation, so EKK means that you have actually the summation. I hope this is clear. So this relation can be inverted. We can write it in terms of EIJ, in terms of sigma ij. And since we are going to use it very often, we should write it down. So EIJ is 1 over 2 mu sigma ij minus lambda over 3 lambda plus 2 mu sigma kk delta ij or we could write it in terms of the familiar looking Young's modulus and Poisson's ratio. So E is of course Young's modulus. And mu is Poisson's ratio. And what are the dimensions of the Lammers constant? Just like E, right? They're like a stress. So E mu lambda. Oh, what happened? Have the same dimension as a stress, and you all know that nu is dimensionless. And of course there is a relationship between these two sets of parameters. I'm not to make a mistake here. Because we have two independent parameters and we can use either combination. Yep. There is another constant which is also important, and that's the bulk modulus. Any questions? I assume you are familiar with that, so we just go through faster. So the other constant which is important is the bulk modulus. So if we consider dilatation, you remember dilatation, the definition, what it was? What is it, Prabha? It's a volumetric strain, which is the trace of strain tensor, right? Okay, exactly. Everyone remembers, that's great. So if we consider the dilatation, and you all said that it has something to do with volume change and it's the trace of the strain tensor. So you can very easily use the relations that I just showed you. If you just equate I equal to J, you're immediately going to get that. You find a relationship between the trace of a strain tensor and a stress tensor. And a little bit earlier in this class, I defined a parameter called pressure. So now we want to use that. I told you that this is going to be useful. And now if I just substitute from above, then this will be, now I'm writing now a stress in terms of a strain. Shouldn't be very hard. I said it's not going to be hard. Right? So this is the relationship between pressure and dilatation, which is volume change, right? So what connects the two has a name. So people use kappa or K in depending on the context you look at, and this is called bulk modulus, which relates then the pressure to the volume change, right? And you can see from what I have written up there that the relationship between bulk modulus, Poisson's ratio, and Young's modulus. So this is called Now looking at this relationship, so this is relating volume change to pressure. If you have a material, let's say a piece of material with Poisson's ratio equal to 0.5, can you squeeze it? Is it no, or is it a conditional no? So if you put here 0.5, the bulk modulus will be very large. That means that you can't squeeze it. But my question is, if I ask you this question, let's say in the candidacy exam, if it comes like, if you have a ball made of some material and Poisson's ratio is 0.5, could you squeeze it?
No.
Exactly. So the condition that you have to put there is everything that you have seen here, the linear elasticity. This is not true for all sorts of material models. Everything we are doing has all these assumptions built into that. Small deformations, what else? Small deformations is the main thing, right? And linear elasticity, this this is linear elasticity. I told you we cannot have residual stress, we can't have rate dependency. So if you have some unknown mysterious material with a Poisson's ratio equal to 0.5, imagine that that material is such that the Poisson's ratio is defined for that, right? Then you cannot just say, well, I can't squeeze it. So remember, whenever you see something, don't forget the context of what we are talking about. Yes, everything. You remember how we went from the 81 to 21 and then to 2? So all those are embedded in that, and that's what I wanted to emphasize here. This is kind of similar, remember this infinitesimal rotation? I told you cannot just say, it's going to be, you cannot separate the rotation from a strain for any given strain tensor. It's only valid if everything is small, and I showed you painstakingly. I showed you that L is equal to L prime only if things are really small. Otherwise, everything is going to fall apart. So, and one more thing before we go is looking back at sigma ij in the concept of isotropic, homogeneous, linear elastic material. If we have pure shear, what would be dilatation? 0, right? So in that case, we only have the first term left, right? Do you remember what we called 2 times Eij if I is not equal to j? Some engineering shear strength, right? So this mu, what is this then? Have you seen this before? Yeah, it measures change in angle, but this is an elastic constant which is relating the shear stress to shear strain. Shear modulus. That's what I wanted to hear. Great. So I guess this is a good point to start. So next time we talk a little bit more about energy, and then we'll start solving boundary value problems. Any questions, concerns, complaints?